Okay, hello and welcome. 8.4, we get into the area of a triangle. Just a little note, in this section we will use K as our area. The reason for that is throughout the rest of chapter 8, A was used to denote angle A. So the general format for finding the area of a triangle, you've been using it for many years. Half times base times height. Quick little proof there. I almost got a little mixed up there. So we start with some arbitrary triangle and we will construct an altitude of length h as shown. And then we're going to construct triangles 1 and 4 to form rectangles. So we're going to call these guys 2 and 3. So we're making this a rectangle, so a nice pretty right angle there. That will be triangle 1. Similarly, making another little rectangle here, we'll make this guy 4. Now area 1 is equal to area 2. There's any number of ways that you can prove that. You could use alternate interior angles there, and the reflexive property on this guy, alternate interior angles again, and we have angle side angle. That'd be the quick and easy way to do that. Similarly, area 3 and area 4 are the same. And our total area would be the base times h, the height. Since those two are equal and these two are equal, then area for 2 and 3 total would be 1/2 of the base times height. So a quick run through, just applying that fairly straightforward one, and then we'll get into Heron's formula. And my triangles in this section are not necessarily going to be to scale. I'm sure most of you are used to that by now, though. So I'll make angle C 42 degrees. Angle B is unknown. Angle A is unknown. So I would like to have the height of this triangle. They didn't hand it to us, but lucky us, we know some trig, so we can find it. So height is what we want. Well, opposite over hypotenuse, that sounds like the sine to me. So sine of 42 degrees is worth h over 5. So then our height is 5 sine 42 degrees. So our whole base is 8, so then our area would be 1/2 times the base times the height. So our area would be 20 sine 42 degrees. And that would be in square units. If you'd like to approximate, that's about 13.383 square units. All right, so next up, Heron's formula. Basically, if we know the 3 sides of a triangle, but we don't know any of the angles at all. So we have sides A, B, and C. Like before, we're going to construct a height h, a nice little altitude there. And C, we're going to split into length m and length n. So some relationships, and I'm going to number them since we're going to be referencing them quite a bit in this proof. M plus n is equal to C. And then the Pythagorean identities that we have from the left triangle and right triangle. So on the left triangle we have m squared plus h squared is a squared. From the right triangle we have n squared plus h squared is b squared. So what we'll do is start by working with m, where we had n plus n is c. And we'll go ahead and square both sides. So if these two are equal to each other, their squares must be equal to one another. So m squared plus 2mn plus n squared is c squared. We can also do a little rearranging. We can get the m squared alone. So m squared we can say is c squared minus, let's see, there's an easier way for this one. Let's see, yeah, let's do this easier way, my apologies. So we'll use the m plus n is equal to c, but we'll go ahead and rearrange it. This way will get us there a lot faster and easier than that way. My apologies. So we'll get the m by itself first. C minus n. So m squared is c minus n. Quantity squared. So m squared, c squared minus 2cn plus n squared. And what we'll do is go ahead and add h squared to both sides. So m squared plus h squared is c squared minus 2cn plus n squared plus h squared. And then we can do a little substitution. So m squared plus h squared, that is by equation 2, the same as a squared. C squared minus 2cn, n squared plus h squared, that is b squared. So now what I can do is basically solve this thing for c. Or my apologies, for n. N would be easier, more useful. So 2cn is worth b squared plus c squared minus ra squared. So I went ahead and put the positives in the front, negative in the back. So then n is b squared plus c squared minus a squared all over 2c. We'll call that equation 4. So by combining 3 and 4, h squared is b squared minus n squared. So h squared is b plus n by b minus n. Just factoring it. And we can plug n in. So h squared is b plus b squared plus c squared minus a squared all over 2c. b minus that whole mess. So h is equal to square root of, and we can just kind of get a common denominator going. So we have two BC plus b squared plus c squared minus a squared all over 2c. So we just multiply this guy top and bottom with a 2c. And we do the same thing with our next guy. Two BC minus b squared minus c squared plus a squared. So just distributing it, it flipped all three signs all over to Charlie again. So square root of 2c by 2c, we'll kick out a 2c there in the denominator. And we can do a little bit of factoring here. So we have b squared plus c squared plus 2bc. Well, that is b plus c quantity squared. Minus a squared. Similarly, on this other guy, we have a squared minus b minus c quantity squared. So we can factor those guys out again. B plus c minus a, b plus c plus a. So difference of perfect squares. Same thing with these guys, difference of perfect squares. So a plus b minus c by a minus b minus c. And since it's a minus that quantity, that'll flip sign on that fellow. And we still have our 2c at the bottom. So our total area for the triangle, 1/2 times the base times the height. All over 2c here. So notice the c's outside will drop. So then we do a little bit of substitution, and a plus b plus c over 2, we refer to that as the semi-perimeter. So then S minus A plus B plus C over 2 minus 2A over 2. So I just got a common denominator going there. So that's our B plus C minus A over 2. And you can construct similar ones for S minus B and S minus C. So then we get to K lands us at semi-perimeter times semi-perimeter minus A, semi-perimeter minus B, semi-perimeter minus C, all under the square root. That's a little bit longer than what I'll ask you to recreate on a quiz or a test. So I did sort of condense a little bit on the last part. So putting this to work, let's say we have a triangle and its sides are 3, 6, and 7. So we know that this triangle can exist since adding up the shortest two, we are still longer than the longest side. If you add up the shortest two and you come up shorter than your supposed last side, you don't have a triangle. So then our area, square root of, so finding the semi-perimeter, 3 plus 7 plus 6 all over 2, so 16 over 2, and our semi-perimeter is 8. So then we have 8 by 8 minus 3 by 8 minus 6 by 8 minus 7. So semi-perimeter minus each of the sides in turn. So K would be square root of 8 by 5 by 2 by 1. So K is root 80. So that's root 16, root 5. So 4 root 5 square units. So without knowing anything about the angles, just the lengths of the sides, we do know the area then of that triangle. So in 8-4, I would recommend 1 through 39, the odd problems. For those of you reading ahead a little bit, we are not covering section 8.5. We don't cover that in this course. So you'll want to skip ahead into chapter 9 if you're reading ahead. If you have any questions, please get in touch with me. Otherwise, I'll see you next time.